Good morning, Kyiv. Thanks for being here. Yeah, I want to talk about 3 common pitfalls in microservice integration today, and obviously also a bit about how to avoid them. Just a quick poll. Who of you is already doing microservices? Oh, wow. In production? More than one service? Okay, awesome. Wow, that's quite a huge crowd. Who of you is doing serverless, like function as a service, Lambda or Azure Function or whatever it is? Okay, quite a few here. Okay, that's interesting. Who is doing at least, let's say, one REST or SOAP call somewhere in the architecture? Okay, yeah, we covered. That's like the normal picture, and that's what we're seeing a lot. And actually, this talk could have also been named like integration challenges in distributed systems. But microservices is a better marketing catchword at the moment. So we're basically, everything we do nowadays is moving towards distributed systems. And I always use this metaphor for distributed systems. So whenever you build like one microservice, one service, like one program, you're in that small hut over there. And it's relatively cozy to be there. You can program in one programming language. You have probably asset transactions. You know what your threads are doing and so on and so forth. So there are a lot of advantages of being there. It's fun to be there. Whenever you open the door, then you will see that the rough ocean. And the rough ocean, that's the network. So you will face a network. And the network, you probably know the fallacies of distributed computing. And the first is the network is reliable. I mean, if you're, no offense, I know it's hard to get it running, but at the moment, if you use the Wi-Fi, you will see the network is not really reliable always. And this faces or imposes a lot of problems on developers, which very often they're not aware of. And that's what I wanted to talk about today. And I've written an article on InfoWorld earlier this year. So if you want to read it up later on, probably just go there and basically you can read about it as well. And the 3 pitfalls I selected are basically around what I just said. Remote communication is quite hard. Asynchronicity has challenges. And distributed transactions, like getting consistency into this world of having distributed components is quite hard, actually. Okay, let's do that. Obviously, like every human being, I have my own biases. I have my own opinionation. And I wanted to make it transparent that you get an idea what's my background and how, or what's the perspective I take on certain problems. And I'm co-founder and developer advocate of Camunda. We're an open source workflow engine vendor, basically. We're based in Germany and have offices in the US as well. And I work with workflow engines and state machines since basically all my professional life. So that's more or less like 15 years now. I contributed to various open source workflow engines over the last 15 years. So in my current daily job, I'm travel around either giving like talks like this or writing articles, but also doing a lot of like solution designs or proof of concepts at customers. So I really try to understand their problems and map this to solutions. But I always do that with having state machines in the back of my mind. And so I also look to these kind of problems with the remote communication with the perspective of state machines. That's probably interesting. And then, but that's very, like all over industries we're working, for example, for Lufthansa or T-Mobile or Sberbank, so it's really not related to any certain industry. So if we jump into that, so let's assume you have an environment of various microservices. One thing, and that's a mind shift, it's probably already pretty familiar to you, but a lot of people are not really yet aware of that fact. There's one mind shift which is really important, and I'm not sure if you can see that here, but that nice little fire down there. So what we have to accept actually in these environments is that some parts of the system will always be broken. It might be the service itself, but if it's not the service, it might be the network. The network connection towards the service might not be reliable. So you always face situations where some things are not working as you expect in the system. That's status normal. But what we have to avoid, and that's about resiliency, and that's very important and getting very important, is that this cascades through the whole system and basically brings everything down. Right? That's the thing you have to avoid. So some parts will always be broken, but you shouldn't let it get down the whole system. Okay? That's important. And I make an example. I'm an example guy. So I'm using Java and Spring Boot today for the example because I want to dive into code. And what I do is I do a payment service. So let's assume somewhere in the company you want to retrieve money for certain services or order fulfillment or whatever you do. And let's assume you accept credit card payments, then probably you don't want to do the credit card handling yourself, but you use like a downstream service, probably somewhere in the cloud, in the internet. It might be something like Stripe or Wirecard, or there are different providers doing this for you. And then you most probably leverage a REST API. That's easy to imagine, right? Okay, cool. So let's do that. Who's doing, I don't ask for Java, who's doing Spring Boot here? Okay, wow. That's quite a lot. That's cool. So I have Spring Boot here as well. So, and the first thing, yes, this is Eclipse. But it doesn't matter. We get that with Eclipse, don't worry. So if I do it in Spring Boot, and I hope that's readable even in the back. Yeah, okay, cool. It looks a bit normally like this. I have the REST controller, then I provide a method. In this case, I want to have a put on a certain URL. That doesn't matter too much at the moment. Then I probably do some like data mapping, which is kind of nonsense for the example. But then I do the real work, like the business logic. And in this case, it just means charging a credit card. If I do that in Spring or in Spring Boot, I might use the REST template from Spring, post something to a certain URL. The URL might be discovered by whatever Spring Cloud from a registry, or I don't care at that moment, but I get it from somewhere. I create a request as a kind of an object, send it over, and they do all the things, transforming that to JSON or whatever. I get back a response that's unwrapped into an object, and I get that back, right? So this is more or less the code. Everything I showed today is on GitHub, so you can also check it out later on or run it later yourself. So that's, let's say, a very typical thing you probably also have done in the past. I have that running in the background. So I started up that thing in preparation. So that's exactly what you can see here. That's my Spring Boot app, which came up. And what I also have is I basically have what I have kind of a fake server for the credit card handling, because I don't want to go to a real credit card handling. I just simulate that. And what I can do now, if I open my Postman, and let's see if that's doable with that screen. Not sure if you know, probably we do it like this. So now I can shoot a request towards it. So I do a put request on that URL. I get back a 200 OK. So that's kind of working. I cannot do it in parallel here, but what you can see, probably I do it like this. That could work. Interesting screen setting here. So if I go like this, if I fire it, you will see that there's a credit card charge over there. That's probably not so awesome, right? But what we can do, we can make it more awesome. So what I could do is I could switch that down. That would mean that like the service is broken or the network is broken. But that's kind of easy. Then you get an exception, you get a 500. That's kind of easy to imagine. But what I want to do, and that's more interesting, I want to make it slow, behaving slow. So that could be the network is currently behaving slow for whatever reason. And slow is much more interesting than it's not available. What happens if I press the send button? Let's see if somebody is following me. What happens? Sorry again? A timeout? That could be, that depends a bit on the situation that you cannot probably tell because I haven't shown you all the code. So let's do it. So what I do, probably it's not behaving, oh, no, it's low. Probably it's a random delay, so probably the random was 0 seconds, so that's not a delay. But now it's 40 seconds. And what you can see here, it's blocking. It's blocking. I mean, that means I do the request towards the payment service. The payment service is blocking while waiting for that response. That's kind of logical. Probably you get a timeout after like whatever, 60 seconds, depending a bit on what you're doing there. But why is that so bad? That's really bad. That's exactly that picture. What we did is we had the payment, the credit card service. It didn't respond. Now we're having my payment service. The payment service normally has a thread pool. All the threads are blocked by waiting for the credit card service, meaning this gets unresponsible after a while. And then we have probably another upstream service like an order fulfillment thingy, and that gets unresponsive. So we're doing exactly this cascading thing. So that's a pretty bad idea. Anybody has an idea what we can do about that? Async is a very good recommendation, actually. I come back to async later on. I want to keep REST for a second, but want to safeguard it. Probably you have heard of the circuit breaker pattern. Some of you, yeah, I see some people nodding. That's a very important pattern, actually, basic pattern. It works like the circuit breaker in your house at home. So if there's something strange with the electricity, before it burns down, or you probably get some problems there, it just switches off. And that's exactly what the circuit breaker can do here as well. I use Hystrix. Hystrix is from Netflix, so it's a very famous library for circuit breaking, but there are others. You can use them as well, but in order to make Java code examples, I have to use one, so in this case, it's Hystrix. So if I go down to charging the credit card, then I changed the code slightly. And the only change basically I did is I wrapped the code. This hasn't changed at all. I wrapped the code into that Hystrix command. I could do that easier in Spring Boot, but this way it's really easy to understand. And that means every call I do is going through Hystrix, and Hystrix can safeguard that. And if it's too slow, it just switches off. And then it doesn't even do like more calls, but really failing very fast at that moment. So that's kind of a basic pattern. How does it look like? So if I have, sorry, no, that was the wrong one. So I have my credit card, still slow. I have my payment service here. I do a put on V2 now. What you can see on the left, it's still slow, so it will take 50 seconds. What you can see here is that I get an exception. That's from Hystrix, relatively fast, that's configurable. And here you can see I'm going to a 500. So I'm really getting an exception here on that level, okay? So that changes the behavior. Now I don't like having the slow credit card service taking down the availability of my payment service itself. Okay, that's an important basic pattern. That's relatively well known. That's a circuit breaker. If you don't know it yet, that's important to get to write that in the back of your mind. If you're around for talks, very often there are talks about service meshes. If you're in for example, Kubernetes, they also do circuit breaking. So that's important. That's about failing fast. So these circuit breakers can immediately throw an exception if the network is currently not available. So you don't have to block and wait for the timeout. So that's important. But from what I see at customers in the product, they normally apply that because they kind of know that or read about it. But they keep it like that. And from my perspective, it's not enough. And I want to tell you a short story in order to visualize that. Who has used an airplane before? Oh yeah, quite some people. Okay. But that's good, you know the process. So the process is you book a ticket, and then 24 hours before the flight, normally you get an email invitation to check in. And then you do that, you select the seat, you confirm, and then you're checked in. And then you have a button where it says, send me the boarding pass, because I need the boarding pass when I get at the airport in order to go through to the plane. And I did that for a flight to London last year, actually. It was from Germany, so it's a German website, but that doesn't matter. I could check in, but when I hit send me the boarding pass, I got basically an error message. Hey, there was an error sending you your boarding pass. Okay. What I imagine that happened there, I don't know about Eurowings. They're not our customer, but we have other customers doing more or less the same thing. And I imagine it like this. Okay, that's me in front of some kind of web application, which steers the UI. And then this uses probably a check-in service or microservice, right, doing the check-in. The check-in microservice probably doesn't do everything on its own, but it probably leverages other downstream services like generating the 3D barcode on my boarding pass, or probably generating a PDF I want to print out to take it with me to the airport. Or what I personally totally love, when you're flying British Airways, you can select to send a fax with a boarding pass, which I always wanted to do, but I never did it so far. Then they probably have more services down there, right? And what I imagine that happened is that the barcode generation didn't work, because I could check in properly. That worked fine, but I couldn't get the boarding pass. So I probably something is wrong down there. And they also probably safeguarded that in a way that it didn't bring down the check-in service. So I could click the button. It worked. I got a response relatively fast. It just was not the response I wanted to have. So that was kind of okay. And what I said earlier, if you have a relatively large system, this will be at some point in time always normal. So that's okay that some parts break at some times. But yeah, and for some airlines, that's actually not true. So that's a screenshot from United when I checked in, and I got really this like internal server error. That's like the worst case that can happen. That's when you don't have these kind of like circuit breaking things in place at all. Actually, the good part about that talk, I'm giving that quite regularly now, and when I get errors from airlines while checking in, I'm always happy now in order to collect them. So I have a collection of like 10 or 12 airlines, so I could basically do all of them. But anyhow, but still, what they do is they have the problem down there in the barcode generation, for example, and they bring it back, it ripples up to me as a user. And that's a bad design, actually. That's a bad design. What can I do about that? What will you do? It's normally safe to ask that to developers. It's like, say it again? Frustrating. Yeah, that's kind of frustrating. But actually, no, for me, it's kind of, okay, there's an error. It's kind of normal. We are getting used to it. We retry it. We do it again. In the web, that's kind of the normal thing you do. You just hit it again. But it didn't work. I retried it a couple of minutes later. It didn't work. So the next thing I did is I created an entry in my Outlook, like in my calendar, because I wanted to retry it a couple of hours later in order to see if it works then, which it did actually. But that's what I call a stateful retry. You probably cannot see the stateful here, but it's I just walk you through. So I call it stateful retry. So you retry, but you have to keep the state in order to not forget it, right? And the bad design here is that I, as a user, have to do that. And this is very obvious because I'm a human. I'm even the customer in front of the UI. But this is very often the normal situation if you have microservice to microservice communication. Even if another microservice is your client, your customer, your consumer, he probably shouldn't do that in this case. It would be much better, much better. Oh no, and the best part of that story actually is that on my onwards flight from London, so I had this on my flights towards London, onwards I had EasyChat and I had the same problem. I think that was my first motivation to do that talk actually, because it was on the same trip. And EasyChat, and they gave me the work instructions. They said, we're having some technical difficulties. Okay, recognize that. Please log on again. So retry it. If that doesn't work, please try again in 5 minutes. Increase the retry interval. That makes a lot of sense. And the best part is actually here. We do actively monitor our site. We'll be working to resolve the issue. There's no need to call. It's your problem. Solve it yourself. Yeah? We don't care about that. And that's really written down like what I had on slide before. It would be much better design if they say something like, hey, we're having technical difficulties. It's our bad. But please understand, we have that from time to time. But we take care. We send you the boarding pass right on time. The boarding pass is asynchronous anyway. Get an email normally or a text message, or I get it in the app. I don't care if I have it in the browser. I want to click the button. If there's a problem, I want to get it on time. Right? So they should do the retrying themselves and then probably also keep it like a stateful retry, but directly in the check-in service. That's something like, okay, we do it, we promise you we will send it, and then they should do it. I think that's a much better design, and you can make the same case for a lot of examples, even to service communication. Okay. When I discuss that with teams, normally they're kind of buying that after a while. Okay, that makes my architecture easier. It makes my API cleaner. There are a lot of advantages of doing that. But that's stateful. Stateful, that's kind of bad. I mean, handling state, that's kind of painful, isn't it? I mean, it's 2018. There are manifold ways of storing state. It could be a database table. It could be a persistent document if you have it, or persistent actor if you do these kind of things, or whatever. There are really many ways of storing that. The problem is if you store that, like send a boarding pass later, you need additional things like something that polls regularly in order to resend it or to retry it. You probably have to have some monitoring in order to see what's going on and if something is stuck and so on and so forth. If you change the way of sending boarding passes, like you change the program and you still have ongoing retries, you have to think about versioning these kind of things and so on and so forth. So a lot of projects back off this idea and say, hey, this is a lot of complexity. We don't want to do that. So let's just like that's a hot potato. Let's just throw it to the next service. And that's bad behavior. The other alternative, and that's actually what I said, that's my background. I'm coming from state machines, or most of the time they're workflow engines nowadays. They can be used for exactly that problem. Whenever I propose this, normally the reaction is like, oh, workflow engines, really? Are you serious? These are kind of like these BPMN systems from the big vendors, like these unhandy proprietary things like from the past. We don't have that end-to-end business process we want to automate. We have that one REST call and we do 30,000 instances per second. That's not for a workflow engine. And this perception is not really true anymore. So there are a lot of like misconceptions about these workflow engines. And that's actually interesting to look at the workflow engine market as of 2018. So if you look around, what do you see? For example, if you look at the cloud vendors all are doing some kind of a workflow engine. So in AWS, it's step functions, or for Azure, it's durable functions, or for Google, it's basically Apache Airflow. So all of them are doing something in that field. So that clearly shows the requirement for these kind of tools in that architecture. So if you look at the Silicon Valley stacks, like for example, you probably can see that, but down there it's Netflix Conductor. That's an open source project from Netflix. It's a workflow engine. Or Uber did something called Cadence. Or Airbnb did Apache Airflow. So all of these companies they're inventing something because there is really a need for these kind of things. The problem with these tools normally, so cloud only works in cloud, and these tools normally are very opinionated in the way they're built. So Uber, for example, uses Go and Cassandra. If you're not in Go and Cassandra, that's kind of, you're out of luck there. But especially in Java, and that's the good news actually, in Java there are lots of frameworks, most of them open source, which you can leverage in order to do that. And even on a high scale, I'm not talking about that today, but that's a very interesting thing actually. So what we're currently doing, we're having an open source R&D project where we currently built a horizontally scalable workflow engine where it can even run like 1 million instances per second. So technology-wise, that's doable. But I don't talk about that today. But I want to make code examples again. I want to make it concrete. I want you to understand what kind of complexity you should expect. And therefore, I use Camunda, that's the open source product we do. But in your mind, you can totally compare that to like other lightweight open source workflow engines. So like Hystrix, there are other options, and for Camunda as well. But I want to show you what I mean, and then we have a good basis to move on. So we are still having the Stripe fake server, and we have the payment service. Let's go back to the code for a second. So we were in V2. What you can see is I have a lot of versions here, so we don't go through all of them, but we go to V3. What's V3? V3 now uses a state machine in order to do that stateful retrying I'm talked about. So what I do here, I auto-wire the workflow engine. In this case, it's very easy because there's a Spring Boot starter, so I just have a Maven dependency hooking the workflow engine in as kind of a library. That's an important thought. It's not something running somewhere, it's a library, it's just part of the Spring Boot application. Here, I wire it in. Then I define a kind of a workflow model, a state machine model, where I say, okay, this is an executable process. It starts here. Then I have like something to do, which is called a service task in the language I use here, which is BPMN. And I attach code to it. And if I'm in Spring Boot, attaching code means I refer to a Spring Bean, like the Stripe adapter, that's here. That's a Spring Bean. I think we have a small delay there, so I hope you can follow. So that's the Spring Bean, and the code in the Spring Bean, it's exactly the code I had there before, right? That doesn't change, didn't change at all. I just moved it to that Spring Bean, which I then could link to my workflow model. And then I'm done. That's a very tiny, very easy workflow, but it gives me a persistent workflow. And that means whenever this fails, for example, I can do something like, which is called here a failed job retry time cycle, that retries it 3 times with a delay of period time 1 minute. But you could do what I had in the boarding pass example earlier on, retry it for a couple of hours. That would be easy to do here. And then you deploy that workflow model, it gets versioned and so on and so forth. I'm not really talking about that today, actually. And then when I charge the credit card, I'm no longer directly invoking the REST call, but I'm basically kicking off a new workflow instance, handing over the data it needs, and then it does it in the background. Okay, that's all the code you need. Again, it's on GitHub. You can read it up later on as well. But I think you get an idea what I have to do in order to get it going, more or less. So let's do that. They're still working. So that's now v3. If I go to v3, my stripe fake is still slow. So Hystrix should still switch off. So we'll see 23 seconds in my payment service. You will see an exception, so everything like we expected. But here, I don't get a 500 anymore. I don't get an error anymore. But what I get is an HTTP 202 accepted. So, and if you're in HTTP response codes, I think that's a very important one. So 200 means, yes, here's your response. I did everything, here's the result. 202 means I got the request, I will figure it out, I will talk to you back. That's kind of the first step towards asynchronicity, right? So I don't get an exception anymore. That's better. I mean, we send you the boarding pass, we promised later on. But in the background, it didn't work because the stripe fake is still slow. So what you can see is that these kind of tools, they keep the state, and they normally have a way of looking into that. That depends a bit on the tool you use. But in this case, for example, I can look into it graphically, and I see, okay, that's currently waiting here, and it's still doing the retries. I could shut down the computer, bring it up again, it's still persistent. So that's currently going on. After a while, when the retries are used up, we get like a red mark here. Hey, this is not going to work. Some operator has to fix that. Okay, so that's going on in the background. Normally, when we're at that stage, when I discuss this, people say, okay, that's kind of interesting. Yeah, I buy it, that's better now, but this is 202 accepted. That's asynchronous. We definitely need a synchronous response. Like, for example, the guy clicking on checkin wants to have the PDF directly in the browser in order to print it out, right? That's very often a requirement. But that's easy to do, actually. So if I go to v4, what it does, it doesn't change at the first step. It's still 202 accepted. But my stripe fake, my credit card handling is still broken. Right? So that's really slow. So it cannot give me a synchronous response. It just doesn't work. Something in the call chain is broken. But if it recovers, if I bring it back to normal, and now send a new request, what I get back is a 200OK. So if everything is like working smoothly, my happy path, then I can get a synchronous response. That's fine. And depending on what my computer is currently doing, that's normally even not slower than I do it normally. That's another misconception people have. If you introduce like all these kind of things like Hystrix or a state machine that gets slower, it doesn't, right? So that's pretty fast actually. And that's now, I think, a really good behavior because that's as good as it gets. Because if something is broken, I cannot deliver that synchronous response. So the decision really is, do you want, in case something is broken, do you want a synchronous error message towards the user or an asynchronous result? And I'm, as a user, I definitely know what I want to have before I get the error message. We can send you the boarding pass, or it's asynchronously, like via email, the boarding pass. That's a much better behavior. Okay, so far so good? Cool. Let's move on with that. So what we have now, we have the payment service. We have like a simple state machine, a simple workflow running embedded in that payment service and calling it credit card. That gives us the persistent state, so we're very reliable. We can really retry that for even like long times. Awesome. If you do retrying, and you will do retrying, even if you're not like doing stateful retrying like I proposed here, you will have retries in distributed systems, for sure. You cannot even control that sometimes. So there will be retries. One important thing to keep in mind, if you have these kind of retries, your service providers have to be idempotent. Idempotency means, in this case, for example, if I say charge credit card and I say it twice, it doesn't charge the credit card twice because you have some kind of correlation ID or whatever you use in order to detect duplicate calls. Idempotency is really important. So that's one of the most important things actually to keep in mind. I make an example of that. Like, I always like to look at these kind of things from a consumer perspective because that's easy to imagine. And I take this example. So again, airlines, United. So I had that once where I did something there, and then when you pay, and you probably know these kind of pages, when you pay with a credit card, it does some loading thingy, and then it says your transaction is in progress. It may take up to 60 seconds to complete. Please do not close this window or select the back button. Some evil part of my brain normally says like, I want to hit the back button and see what happens. But then it's like, it's my credit card, I don't do that. But I normally book things in the train. I have no idea about Ukraine, but in Germany, the Wi-Fi is really leaky in the train. And then you do this, you see it, you see the tunnel, and you think like, oh God, man, do it faster. So it makes me really feel bad. And that's the same thing. It should be like, hey, you want to give us money, that's awesome, we want to have that, but we make it as convenient as possible. We generate whatever, a transaction ID, store that locally in your browser. You can even close down your whole browser, start it up again, and everything works. Right? And that's the same thing for service-to-service communication. You should really think and care about these kind of things. That's my favorite slide, actually. I like this slide. Took me quite a while. No, there was a vegan part in my life, so 5 years back, more or less. I ate vegan for 4 or 5 months. Then I gave up, basically. But now I have kids, I can do that. Can't do that anymore. But there's an awesome dish which I really loved. So what you can do is you can basically take a zucchini and slice the zucchini. There's a special slicer. Then you get noodles out of the zucchini. So the zucchini is then the noodles, and then you add some sauce. And then you can eat it, and it's really delicious. I totally recommend that. In the book, it says you can eat as much of the dish as you want, like because it's very healthy. You don't grow fat. It's one of the things which is allowed in the evenings, and so you can really eat as much as you want. So since then, I started to use that as a metaphor for idempotency, actually, because if you ate your plate of zucchini, you can just eat another one. You can just eat another one. So it's totally idempotent eating zucchinis. And that's very different to eating pasta, right? Eating pasta is not idempotent because you will recognize the second portion, right? So if you have a better metaphor, I'm happy to take it. But that's the one I use. And if you only want to take away one thing of that talk, I think it's about idempotency. If you do your microservice, if you provide an API, make sure it works idempotently. It will make the world, let's say, a little bit better. So that's really important. Okay, but we're not yet done. We're not yet done. We're still in distributed systems. So let's assume you want to charge the credit card. So over there, we charge the credit card. Whoa. With a delay, that's really hard to do, actually. We charge the credit card here, and we even do the retrying, but after a while, we might give up. It might be time controlled, or we say we have used up all the retries. So we give up, and we send out that payment failed event saying, okay, this is not going to work. We have to cancel your order, or whatever it is. We're in a distributed system. Distributed systems have one characteristic which is really bad, actually. So let's assume you're doing a REST call and you get a network exception while doing the REST call. Then you have no idea which of the 3 scenarios happen. So the first could be you have the client and you never reached the service provider because something in the network was really not working. The second possibility is you reached the service provider and exploded while processing your request. And then you have no idea if he committed the transaction or not. Or he probably did everything as wanted, but then the response got lost in the network. And you have no idea what happened. That's a problem. You can do the same thing with asynchronous messaging. If you send out a message, like you push it on the message channel, that worked, but then you don't get a response back. You have no idea what happened. That's just not possible to know that. And you have to tackle that. Probably not in every use case, but especially if you're caring about payments, it's probably not a good design. Customers will not love you if you give up, say payment failed, you don't get your order, but you charge the credit card. That shouldn't happen. So in this case, you have to think about the situation, and you, depending a bit on what the API of the credit card can do, you either ask if it already was charged, you probably cancel a charge, or you refund it, whatever. There are a couple of possibilities, but the important thing is you have to do it, you have to think about it, and I mean, if charging the credit card was not really reliable at the very beginning, like canceling the charge or refunding might probably also not be available. So again, it's very important to have that persistent, to have it reliable. Okay? Good. What I'm using here is BPMN. I just had that in the code very, very briefly. It's an ISO standard. It's a language for defining these kind of state machines, and I definitely love BPMN. So I wrote a book about that quite a while ago. So, but I'm not loving it because I now have the book and I have to love it. But it's really a good language. It's really a good language for expressing these kind of state machines, and it's relatively widespread. That's a good thing. It's directly executable, so you saw I even defined it in code, and it's easy to understand for different stakeholders. So especially like for operations, if you think about operations use cases, like you're probably stuck in charging the credit card, you can see something like, okay, there are 317 instances currently stuck. And an operator not knowing anything about programming can probably look into that, see the data attached, see all where it's coming from, fix it, retry it, and these kind of things without really knowing what he's doing there in detail. And you also get a lot of like statistics, for example, and this also visible for stakeholders, not programmers. That's very different if you look into a lot of these tools you have out there now from, for example, AWS or Apache Airflow. That's really like very low tech. You don't get this visual at all sometimes. And they're really reinventing the language. So a lot of things which are in that language defined are really well thought through. So independently of what kind of tool you want to use, I would recommend to have a look at this, at BPMN at least. And then I go focus on that today. So there's a blog post. The slides will be on my SlideShare account later on, so you can see it on SlideShare. You get all the links there, so don't worry if that's probably not readable here. But there, I have a blog post on architecture options to run the workflow engine. Just to give you the high-level intro to that, so what we saw today is that we have our payment service as a Spring Boot application, and then we can just embed the workflow engine as a library in that service. If you have another microservice, that probably has its own engine. This way, it's totally isolated. They can select their own products. They can run it as they want to. So it's really like, in a way, in the microservice mindset. If you're running something else than Spring Boot, if you're running Wildflower, WebSphere, or whatever, you can also do this, depending on the tool a bit. So it's comparable. If you're not running Java, you probably have to run a workflow engine remotely, because in most of the languages you don't have that. All of the really working ones are written more or less in Java, and that means you have to connect remotely, but also that it's easily possible. Okay, cool. So we talked about synchronous communication so far, and at the very beginning we had the recommendation, probably you should look into async, and I totally back that. So my favorite quote when talking about synchronous communication is actually this one from Todd Montgomery and Martin Thompson. They're really building a lot of highly distributed, high throughput messaging systems, so they know what they're talking about. Synchronous communication is the crystal meth of distributed programming, and that's the thing. If you're doing a REST call like I did in Java, it looks like a local method call, right? It was so easy to do. I get a response back. It was really like locally. But the thing is, it's not local. It's totally not local. You have all these network things. You don't have transactions. I talk about that in a minute. There's a lot of complexity involved, which is kind of hidden there. And that's why a lot of people love using it. Kind of, oh, yeah, we should think about that. Yeah, probably asynchronous would be better in that way. We know, but we have a tight deadline, and the last time we do it today, tomorrow we will improve, and that's kind of the thing, right? So looking at asynchronicity. But if we do that, actually it doesn't change that much. So let's assume the same check-in example. Let's say we have a check-in microservice. It sends out the message towards a barcode generator to generate a barcode for us. Then what we probably know is that this will more or less work, so we don't have to retry it. Because if the peer is not available, we can still put or push the message in the queue. That's a good part of it, right? Temporal decoupling, that's awesome. But we still can have a situation where we don't get a response back, right? We're waiting for the response, like the barcode, but we don't get it. And then again, we have no idea what really happens. And normally, you have to take care about these situations, because it should not be the user here which has like looking on the watch and say, hey, okay, now like 5 minutes later, I should have it, right? So it should be, again, the check-in service monitoring these kind of timeouts. And then again, you can do that with these kind of state machines. Like if you're looking at BPMN, for example, it looks like that. I could send out like a message on a message bus. And the next thing I do is I wait for the response. This is again like stateful, it's persistent. I can wait for hours or days or weeks or months if you like to. I wait as long as necessary for the response message. And then I can even handle the notion of time. Something like this means whenever, like in this case, every hour, if an hour has passed, I do something, like for example, resending. That's a retry on a higher level, let's say. And this one, if you have good eyes, you probably can see that as dashed. And dashed means I do that additionally, I keep waiting. So this is something you can easily do. And you can probably even do more. I'm not sure if you can see that down there, but what I have here is like another thing where I say whenever it's 4 hours before my flight, so independent where I am in that process, if it's too late, I probably do a plan B. That also happened to me. I have like a text screenshot from Virgin Atlantic. They send me a text like, go to the counter, please, right? That's kind of okay. I mean, it's better than if you promise it, you have to deliver in some way. If you can deliver here because something is broken, you have to think about how to degrade the system. And you have to constantly think about that. And a lot of the solutions you need will involve some kind of state handling there. Okay, awesome. So we have the timeout for asynchronous. We have retrying on different levels. We have idempotency. Who uses a message bus here? Talking about asynchronicity. Oh, that's quite a people. Keep your hands up for a second. Keep your hands up for a second. Who has no problems operating the message bus? Oh, one, no. I thought one guy, no. Normally, most of the time it's one guy. I think he follows me for the conferences, just to raise a hand there. But normally it's no one, right. I do agree that it's like safe to ask no problems questions. Who has no problems? That's just not possible. But it's surprisingly, often people have really basic problems with this messaging. So if you have a message bus and say you process a message, you get a message from the bus, you process it, you get an exception. You don't have a client waiting, so you can just throw the exception to the client. What happens is that this gets a so-called dead message. You cannot process it, it gets to a dead letter queue. Somebody has to monitor it and do something about the dead letter queue. And there is really a big lack of tooling. Even in the modern tools, if you're using Rabbit or Kafka or whatever it is, you will have lack of tooling in order to really see the dead messages, to see the context. Where did they come from? Why did they end up there? What's the payload? If the payload is broken, fix the payload, redeliver the message. So there are a lot of things which are missing. And that made a lot of customers I know building own what they call message hospitals, like looking into it. A lot of tooling they have to build. And that's quite some effort. Right? And that's a big pity. That's really a big pity. In 2018, I personally, like architecture-wise, I would totally recommend to go asynchronous. I think it makes a lot of sense. But then you have these really basic problems on a tooling level, which is normally a big showstopper for adoption. What I saw a lot of customers doing that in the beginning was kind of a surprise for me that they really do that on a big scale, but it works really good actually. So what I showed so far with that kind of like a state machine or workflow engine, it's kind of a push model. So if I had a service task, there I had the piece of code calling actively another REST service. That's kind of a push. Or if you're using AMQP, probably that actively pushes the message toward the bus. That's always kind of a push thing. What you can do is you can use these kind of tools in a pull model. And the pull model means I'll probably go over there. The pull model means there is a service, some kind of activity which service B could do, and service B asks for work. Hey, is there something to do for me? It pulls for work, right? And then you can build architectures like where you have like, let's say, different activities in your workflow, and then you have different services pulling for work, and that means your workflow engine gets kind of a work distribution in the architecture, probably for this scenario, even replacing kind of a messaging for at least parts of the system. And that works actually pretty well. And then you get that added value of this kind of tooling you have around workflow engines. Okay, awesome. Who has heard of the thundering herd problem? That's normally not many people. Yeah, right. That's good that it can at least learn something. The thundering herd problem also refers to retrying. So if you have a service, like a REST call, what I said earlier, you retry it probably because it's not available. If you have a lot of retries piling up for that, and you bring it up again, you do your own denial of service attack on that service immediately, and that probably crashes it again, right? That's a thundering herd problem. One of the most famous examples of that is AWS. In 2015, they suffered a 5-hour outage of a whole region. That's huge. It's AWS, a whole region, 5 hours. Like important things, that you cannot read the important things there, but affected services like Netflix, Tinder, Airbnb. I think I had Trello not working at that time, so that's quite a huge thing. They did a really good post-mortem on that. You can read it up over there. And I don't go into the details of it, but it was basically a thundering herd. There was a relatively small component which basically crashed. Then a lot of retries piled up, and every time they tried to bring it up again, it was basically knocked down immediately, right? And it took them the 5 hours in order to figure that out. And you can actually avoid these kind of thundering herds if you go to more probably asynchronous. You can still have that with asynchronous depending on the how you do it, but definitely with a pull model. Or you have these kind of, if you know, back pressure. There are a couple of patterns around that. But that's also important to keep in mind, not to bring down the whole system. My favorite thing about that outage is actually it was covered in a UK press thing. And what I love about UK press is that they put this headline next to this picture of Jeff Bezos. He's laughing there. You can probably see him smiling like this. And this is, I mean, that's kind of a disconnect. I love the UK press for that. Anyhow, now we have like 10 minutes left for my favorite topic, which is about consistency, distributed transactions. Let's assume you want to do, like, well, where should I go? Probably over there. Do two things, like in a row, in an all-or-nothing semantics. If I'm in Java, like programming one Java program, that's kind of easy. I do these kind of asset transactions, like in a database, you do begin transaction, or in Spring transaction, or in JTA, Java E, if you want to. You can do begin transaction, do a couple of things, and then either commit or roll back, right? That was kind of easy back then. And now we have these distributed systems making this actually really hard, and I want to look into that. If you fancy it, if you're really interested in that, I have an own talk on that. I called it Lost in Transaction. For example, I gave it back at Java Zone. It's recorded, so you can also watch that if you're really interested in that, because that makes for an own hour if you talk into all the details of that. But it's a really interesting problem. So let's dive into that. Who has heard of XA transactions, two-phase commit? Oh, not that much people. Who uses that in production? One. Who has no problem? No, three. No problems. Oh, one. That's pretty good. You're pretty good. That's kind of unusual, actually. So XA transactions means I take this asset transaction thing to a distributed systems. And that means like two phases. You have to do a lot of technical things on the protocol in order to have asset transactions on distributed systems. The thing is, it simply doesn't really work. It doesn't scale, it's too complicated. There are a lot of indicators why it doesn't work. There are situations where it cannot recover automatically. You have to understand what happens there. So it's a bad idea actually to use this on a bigger scale. If you don't believe me, and I probably cannot go into all the details like in a minute, but there's a really good paper on that, which is called Life Beyond Distributed Transactions from Pat Helland. At that time, he was at Amazon. Now he works at Salesforce. He was at a couple of companies and wrote a couple of really good papers. So I'm a huge Pat Helland fan, so that's really worth the read. And he explains very well why distributed transactions don't scale. And if you want to remember just one thing from that paper, I think it's its own quote. Grownups don't use distributed transactions. So if you're in distributed systems, you shouldn't count on having this for consistency. But you very often have the requirement, then you want to do A and B, and if B fails, you want to roll it back, right? We had the requirement, how to solve that. And one strategy, it's not the only strategy, but one strategy you could use. It's called compensation in BPMN. Or if you're Googling through the microservice world, or probably in DDD, domain-driven design, you will sooner or later find something called the saga pattern. So that's kind of related. And so it's related in a way that this is one possible implementation of the saga pattern. And it works like this. So we have our workflow, and I'm not sure how I do that, probably like this. I extended it in a way that I say, before I charge the credit card, I have some kind of customer credit he has on my account, like vouchers or whatever. So I check if I deduct it from there. Then I check if there's money left I have to collect. If yes, I charge the credit card. That's an own microservice, so this is committed. I deducted money from his account already, but then the credit card still might fail. I probably can't do it, and then I raise a payment failed event. And in this case, I'm inconsistent because I say you don't get your order because we couldn't charge the credit card, but I deducted money. So that's inconsistent. That's, if you're talking about eventual consistency, that's also eventual consistency on another level. So this is an inconsistent state, but I have to make sure it gets consistent at the very end. And either consistency is here when he paid everything and gets his order, or if he cannot pay that, I have to make sure he gets back his credit. And that's what the compensation is doing. So that's a rewind symbol. So it means whenever I'm here at the very end, I throw that, it's called throwing that, and that means all the activities which have these compensating activity defined, the compensating activity will be executed. That's kind of an undo, like a semantic undo of what you did before. It's not a rollback. He probably see that on his account. Or if I retry for an hour, he probably wants to buy something in between. He recognizes, oh, there's money gone without my order being delivered. You probably know these situations from own examples. So it's not a rollback, but I make sure it's consistent afterwards again, right? And you can do that with compensation, even on very complex models, pretty good. And again, it's stateful. So even if whenever you raise the payment failed event, the microservice for the restoring, like the customer credit, is not running, not working, it's no worries. You wait for it until it gets available again. And the workflow engine keeps track of the state of what already happened and what to roll back. That's actually, I think that's a very important pattern to keep in mind for distributed systems. If you're interested in that, that's what I mean. If you watch the other talk, there are other ways of implementing the saga pattern, so I go into more details there as well. But I think that's, from my perspective, that's one of the most interesting ones. Okay, let's quickly look into that, how that works. So we're going back to code a bit. So we still have our Stripe fake. It's working normally, that's good. We have our payment service. I'm directly jumping to V6 now. So in V6, the only thing I do, basically, I changed the workflow. And this time I don't do it in code anymore. You saw it in Java code earlier on. So I love using the Java DSL at the first moment, because normally I very often saw that developers are kind of afraid of graphical models, or there's some hidden complexity, or it looks like UML or MDA or whatever you hated in the past. So I start with code. So you can definitely define these kind of things in code. But if it gets more complex and you're jumping around, you're doing loops, it gets hard to read the code. And that's why at some point in time, it's very good probably to switch to these graphical models. And then you can model it like in this. And in the background, the XML file, it's in what you saw in my source main resources. So it's nothing really alien in my architecture. So that's a workflow model we just had on the slide. And now I can run V6. So if I do that, my payment service, my Stripe fake should behave normal. I go to V6. I call that. Oh, I could get back a 202 accepted. Why is that? That's bad, right? 202 accepted. So let's look into that. What's happening here? So V6. If I go to that, what I see is that I have one instance currently waiting for the customer credit. And that's exactly because I wanted to show you the pull model. So currently there's no microservice. This is working as a pull model. So basically what I say in the workflow model, I say, I'm not sure if you can read that, but I gave it a name, customer credit. It's kind of a queue name, a topic name. And so I'm waiting for a microservice to do that, to ask for work. And I did it in JavaScript, actually. Let's quickly go for that. So if I do that here, yeah, why not? Visual Studio Code is fine, I think. I did it in JavaScript. You could do it in any language. It doesn't matter. It basically goes for the REST API. I thought JavaScript would be the most fun, right? Right? Yeah. I subscribe to the customer credit and say, whenever there's work to do, stream it here, and then call the business logic, which doesn't do that much here. And then this calls me back, the workflow engine, and says, I'm done, right? So that's all the code you need. And whenever I run that, let's do that. Node, no, that's not good. Node index. It will process that one workflow instance which was currently waiting. Okay, so whenever I go back, this should be gone, right? Okay, it's gone. And now everything is back to normal in my system again. That's what I meant earlier. I'm on 202 because something didn't work. But now everything is healthy, so I should get a 200, right? And depending on how I do it, again, it should be fast. And if I do that a couple of times, I have a random error generator, actually, so I should get 500s from time to time. We're too good at the moment. Sometimes I should get 500s. Oh, no. Yeah, there was one. If you was quick, there was a 500. No, the only why I'm showing that is that then if you're, I mean, it's what I said on GitHub, so check it out, run it yourself, you can play around with that. But if you have exceptions, you can see that either of all they're not that common, and then you can probably go into the instances and see for one of the instances, for example, see what was going on, that the undo is called, and these kind of things. So you can play around with that and make it more visual. Okay, so we had the timeout, the retry, the compensation for undoing transactions. If you're providing, again, if you're doing a microservice, make sure the API is idempotent. Make sure you provide a compensating method. That's very often, if you have to talk to legacy systems, very often they don't have that. That's one of the big showstoppers there. Also, very often they also don't have that. Okay. And then you're already pretty good in tackling at least the 3 pitfalls I'm talking about today. Very often you probably have to think about state. If you're not doing REST or probably not doing like messaging like I proposed earlier on, but really dive into event-driven system. Not sure, does anybody do event-driven systems here? 1, 2, 3, 4, a couple of people, okay. So if you fancy that, I have the same example extended, so whenever you have the payment, I have that connected also to Kafka, providing really like an event bus and have multiple microservices talking to each other in an event-driven way as well. So there you can very much discuss choreography versus orchestration, by the way. But I don't go into that there today. So if you have any questions about that, you probably want to ask me later on. Or I also have a talk on that, which is available on YouTube. But one thing which is really interesting there, to highlight that, and that's the last thing we want to talk about today. If you have that microservice world, and what I had now like a state machine, included in like one service, like a library, like it's an implementation detail of that order or payment service. Then I also like distribute or like having local workflows and distribute the overall workflow. So for example, if I do an order fulfillment like this one only says, hey, send a message to payment, and then I wait for payment to respond. There are no details about payment at all, but payment might have its own workflow down there because it needs some kind of state handling. So introducing this kind of technology doesn't mean there's kind of a central workflow engine or something central. It just means whenever you have a problem around state handling, it's probably worth to have a look at these kind of things. Awesome. If you think, does anybody really do that? Yeah, quite a lot of customers doing that. One of the most famous ones, they do that also at very high scale, is Zalando. They're doing like every order process on this kind of architecture using Camunda and Kafka. Basically, they talked about that at a meetup in Berlin recently. So this is at least what I can share, probably not readable, but it's more or less really what I had there on the slide. Okay, awesome. So as a summary, be aware of the complexity of distributed systems. That's the one most important thing. It's not a local method call, even if it looks like that, and no strategies to handle it. It could be circuit breaking. That's like a basic, really important thing. Might be back pressure, might be about workflow engines if you have stateful problems. A lot of the problems are actually stateful, so then you should probably think about that. So that's, yeah, that's all I have. Thank you very much. There are all the links. I put all the slides on slideshow later on. Yeah, thank you.